The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Did I do it? Yeah, I did it. Okay, thank you for the introduction. My name is Lloyd. I'm from the University of New Brunswick, and this is in Canada. And for those of you who don't know, you drive north from Maine. So that's where it is. It's one of our smaller provinces there. Today I'll talk about some of the work that I did in past life on column retrofit with CFRP. And you're going, if you were here in the morning session, some of these figures and the testing facility might look similar because this was done at the same time as Eric Jacques was doing the similar work on his slabs. So some similar ties that bind there. So here what I'll do is I'll take you through a little bit on the shock tube testing of concrete columns and the simulation of explosive loads with that. And then we'll talk about the responsive columns under these far range explosive load simulations for different detailing, so if it's a seismic or a non-seismic column. And then how can we retrofit columns with FRP to give that detailing, the seismic detailing, to provide some ductility and to give us some strength. And finally, I'll spend just a bit of time on some newer work that I'm doing on the bond of FRP under high strain rates, and this has implications to blast design. So the shock tube facility, as was shown earlier, it's comprised of a driver where we pressurize with high pressure air, and that's the tube at the back. And that pressured air is held back by aluminum diaphragms, and the diaphragms are burst triggering a shock wave to propagate down the expansion section, which is aptly named. And you could think of this as a confined wedge of the spherical sort of expansion of a blast wave. And then the high pressure air interacts with the specimen mounted at the end of this. It simulates far range explosions, nothing too close to the structure. And as John was saying earlier, it certainly is nothing like the really close detonations that were needing this catchment type of system. So the characterization of a shock load that we'd expect for far range design would be a near instantaneous rise to peak overpressure or peak reflected pressure on our specimen, followed by an exponential decay over a pretty short duration in the order of tens of milliseconds. And then there is a negative phase that may or may not be applicable to your design. In the shock tube itself, here we're overlaying some experimental pressure time history along with the exponential decay curve for 238 kilograms of TNT 30 meters away. And we do see that it is pretty representative of what we'd expect from a high explosive detonation. Now, once again, like before what we saw, if I'm testing a beam type element or a column and I want to load it with this shock tube, I need to collect all the pressure that's coming out at the end of the shock tube and transfer that to the column itself. And this is done with a load transferring device. And here it's a series of beams, as was described, that span across the width of the sheet metal behind it, and unlike what we saw earlier, instead of having a tremendous amount of beams, there are a few beams with extra load points on either side to cut down on some mass here. But it's the same principle as was presented in the last presentation. And then here we can see the same mechanism, and in fact, embarrassingly enough, I guess I forgot if I made that figure or Eric made the figure. Well, one of us made the figure and one of us made the load transfer device, so we'll share. Either way. Now, what I'll talk today about is a group of two sets of columns. One is a non-seismic detailed set of columns, and the other is seismic detailed. So these are the differences between them. And what we're looking at is a control group over here, where so all the cross sections are the same on all of these columns, and the difference between the control and the other group columns within this group is the presence of FRP. We have a column with 10 M bars, which are 100 millimeters cross-section area, 4 of them, one on each corner, a 1/4 inch tie, millimeter hoop that is embedded into the core of the concrete to represent a seismic type of detailing. And these are spaced over the entire height of the structure, so this would represent, say, a first-story column, and they're spaced at every h/2, or 75 millimeters for a 150 millimeter cross-section width. The first retrofit was a confinement jacket of this, and so here the J up here stands for jacket, and the NS for non-seismic. The jacket was a single layer of CFRP, and this is a unidirectional material. This was the same Fife product. I forget the designation of it. And it was wrapped around the specimen and then overlapped for 150 millimeters on one of the sides that is, parallel to the direction of the loading. And the second retrofit was placing longitudinal FRP that was 150 or it would have been about, I believe, 120 millimeters wide, over the entire height of the column, terminating just outside of where the supports would be up here, so it wasn't embedded into the support region. And this was done on the front and the back face of the column. And then the final retrofit was the combination of the two with longitudinal strengthening on the front and back face, and then a jacket provided over top of it. And the same thing was done with a group of seismic columns, and here what we can see is the spacing of the ties is a lot closer in here. We're at h/4, which would better represent seismic detailing for confinement issues. But the rest is the same sets of retrofits on them with jacket or longitudinal reinforcement or the combination of the two. And then the summary of the groups. There was other groups being tested here. That's what the 2 represents, but here are the columns that I'll talk about today. So everyone had the same material properties in terms of concrete strength and the same geometry, and they were all loaded to about 25% of their concentric capacity. This was originally designed to be about 40%, but the strength was considerably higher than the 40 MPa that I was going for. So if we start to look through the controls first off, well, it's going to be one of those presentations. Video-heavy presentation with only a few videos. Okay, well, the difference between the two, there's a couple pictures on the next page, so we'll see this, but both of them had heavy damage at around midspan. These columns were intended to provide some degree of rotational support, restraint at the ends, but it wasn't fully fixed, so in actuality, the higher moment region would be in the middle of these columns rather than at the support locations. And what we see from these is in the elastic tests that were done, so a similar, the load regimen was tested elastically, caused little damage, get a feel for the response of it, and then sort of work our way up until we're just at the onset of damage, and then do a larger test to see what the failure mechanisms are. And this was just purely for an economy reason. What we see is there's essentially no difference between the control columns for seismic and non-seismic in the lower limits. This is because confinement issues don't come into play in the elastic response, and there's nothing like bar buckling. But by the time we get into inelastic response, for the higher pressures we see a considerable difference, at least in terms of the failure mechanism. The non-seismic column had considerable loss of core concrete and reinforcement buckling in the compression zone, whereas the seismic detailing was enough to prevent a lot of this loss of the concrete, to distribute the cracks a lot more generously over a plastic hinge region, and to prevent buckling of the concrete. So it, and here we see this minimal core loss. And this is a pretty sound principle of seismic engineering, in that you would want to allow for some post-peak ductility by providing this detailing. Now, we're interested in how that seismic engineering principle translates into blasts, though. And now, with the first retrofit on this, the jacket under the same pressures as before, what we can see is there's minimal damage to both. In fact, they both perform about the same. There was some deformation, and if we go a little bit further with them, all the way up to a failure shot on this, it gets to the point where, if I kept this video going, the camera tips right over, and I was really nervous when I got downstairs and saw the expensive camera on the floor. That's why it was rocking back. But here, the failure mode is very interesting in this. This is a jacket. There's no longitudinal stiffening or strengthening of this FRP. Instead, it provides confinement to the concrete core, and it prevents reinforcement buckling. So if the column is heavily confined, that concrete, as it starts to reach its F'(C), it can't go anywhere. It can't crush, it can't spall. We can't lose the compression concrete. It's still there. And so it was effective enough to push it all the way until we got reinforcement rupture on the tension face rebar. And this was the case for both the control, or the seismic and the non-seismic. So we've prevented this buckling failure, and we've prevented compression failure of the concrete, and rupture was achieved. And so if we look at the response between jacketed columns and control columns, we see in the early stages there's not really much difference because the effects of the jacket that provide this confinement don't really come into play. But at the later stages, we do certainly see a significant benefit to providing this confinement jacketing. Now if we go and look at longitudinal stiffening with FRP, we see a different sort of failure. And this could be, should be expected. By gluing or epoxying this FRP onto the surface of this column, and then taking into account things like there is a moment reversal over the height of the column, so we switch from positive moment to a negative moment up here. We're ending up with, we barely switch. We end up with the case of a very high moment demand on, and sort of strain demand on the FRP at the top region here. We end up with a high strain demand in the middle at the high middle moment, and the effect is we end up with a significant debonding issue. And once debonding occurs, it becomes very, very brittle. And in fact, we start to see the same mechanisms as the unreinforced column when debonding happens. We get, although it's not evident here, we get a rebar buckling and a significant loss of the core concrete. And on the back face, there's a buckling of the FRP that we wouldn't consider as a structural member in the compression zone anyway. On the front face is this debonded surface. Whereas this is the seismic column, and there's far less damage to it, so it did perform better. But we have a brittle failure mode, and we should probably design away from that. Now, when we combine the two, and this one has a longitudinal FRP underneath that jacket, we see a similar sort of response to the first condition where there's no significant loss or no loss of concrete due to concrete crushing and no bar buckling or anything. But if you look at this, there is a significant residual deformation that happens to both of these columns. And what this implies to me, once we get residual deformation, is there's something wrong with the FRP that is longitudinal underneath it. So, in fact, it did limit deflection, and it did prevent bar buckling and compression failure. But the FRP ruptured, the longitudinal FRP ruptured. And this is, there's a lot to this, a lot of different design parameters you could take. You could add many, many layers of FRP under this, and then would you rupture it or would it debond before the confinement effects of the jacketed FRP was able to hold it in place long enough for rupture to occur? So there's obviously many different parameters that could happen here. But what it does show is that you can gain the benefit of stiffening and then also the benefits of post-failure ductility. And if you're considerate in your design to facts of like what happens if the internal or if the longitudinal reinforcement does either rupture or debond underneath that jacket, how much of a drop in capacity do you get, and can you consider post-debond or rupture ductility as a design parameter or not? Well, this is up to you as a designer. But the added benefit of the jacket is clear here in that it did prevent the failure of the FRP and debonding. So in summary here, we see from sort of best to worst, and this was the same with the seismic, control to flexure reinforcement to jacket and flexural reinforcement. So the combination of both showed the highest performance. But we can say this certainly isn't the end of the story for reasons we've talked about, because this is only one balance between column properties and number of layers of FRP and type of jacket and all this stuff. So here, if we take a step back, and forgive me, I'm from Canada. That's a Canadian joke. We apologize about everything, right? So I'm going to look at some Canadian standards here, but you can be assured that they're very much take inspiration from the work that was done south of the border. So a lot of this stuff would be very, very similar to anything from ASCE or some other similar standards. But if we start to look at the use of FRP for retrofit in blast-resistant structures in Canada, we can see that first off, we have levels of protection, and if we're considering a column, we'd be within the building performance criteria. And now so a structural member rather than some component stuff. And for a column, we should probably be in the, in the higher level of protection to make sure that our structure doesn't come down upon us. But you can choose your level of protection based upon your design parameters. And then at that point, you're set with your response limits, and you're starting to look at how far can I push this column to match with these levels of protection. So if we're dealing with a pure flexure member, you might be governed by a ductility ratio in the lowest response limits, the higher level of protection, followed by support rotations that are measures of deflection, basically. So these support rotations would imply that these types of flexure members would have high measures of ductility, and to the point that it's more beneficial to look at a displacement design rather than a ductility-based design. 15, oh, I see. You make me do the mental math. He tells me 15 minutes into the presentation, so now I have to subtract on the fly. I can do that. I'm a professor. Okay. So if we look at the compression aspect of design, though, now we're more concerned with, is this column going to be able to hold up the rest of the building after the event happens? So instead of being able to design into into displacement-based design, we're limited to ductility ratios. And the basis of this design is what's the ductility defined as first yield of the column. And if we have a non-seismic column after this first yield occurs, then we're starting to get the point where we're going to lose compression concrete, bars won't be supported, we can get buckling and following with collapse. So a non-seismic column is limited in the worst possible case to a ductility ratio of 1. Whereas a seismic column, if we can design to that, we can start to gain some ductility capacity out of this and push it a little bit further. And roughly speaking, we can say that these ductilities would be proportional to a displacement-based design at that point. Very roughly, if we can design to B1 at 1 or B2 at 1, this is twice the displacement and 3 times the displacement. Very roughly. So columns are, if we do appropriate seismic design, we can go a bit further. Now, with FRP, and this is FRP applied for confinement, and versus FRP for strengthening. So for confined columns, we can see that we're allowed to go even further if we properly confine it, all the way up to a ductility ratio of 6. And this is because internal seismic steel will confine the core of the concrete, but not the cover. And whereas external FRP jacketing will confine the whole thing. And it will also add to the confinement effects of the internal steel. So we get heavily confined responses. But as in probably a lot of other places, by the time we start to talk about strengthening, it all falls apart, and response limits are not as well defined, and you're sort of on your own for that. I guess Canada couldn't just pick a number out of the equivalent American code at the point this was developed. This is being recorded. I shouldn't have said that. So let's look at confinement very briefly, and what we can say is that if we jacket the column, we're going to put a confinement pressure onto this concrete, and this confinement pressure comes as we bend the column. So you put the jacket after the axial load's been applied already as a retrofit, and so now you're looking at Poisson's effect only coming when you bend the column. It's going to push out against the jacket, and the jacket pushes back in against the core of the concrete. And this has an effect on increasing the ultimate capacity of the concrete, F prime C, and also increasing the material ductility. And the more you confine it, the better those benefits become. And as we can see, if seismic confinement would act in here, whereas a FRP externally jacket confinement would happen over the entire member. And also, if we prevent bar buckling, we can get beneficial compression steel. Now this has the effect, if we confine it, of looking in moment curvature, we can get a poor curvature ductility with increasing axial load. So the darker the line, the higher the axial load. And this means that as curvature ductility drops, this has implications later on flexural ductility. And then if we jacket this, we get pretty high curvature ductility. And by ductility, I mean once it hits a yield, it can retain that capacity for a large amount. So after the fact here, this is a random column, not one tested here. If we look at a particular column, we can say that the effect of an FRP jacket can increase our displacement ductility over something else if we look at the scale of these things. But it can also increase our capacity if we look at the scale of these. So now let me spend 2 minutes. 2 minutes? Maybe 3. On FRP bond under high strain rates. This is a current project we're undertaking. And so one common test is to cast a couple of concrete prisms with a piece of reinforcing steel inside of it, and then join them together with FRP on either side, pull it apart, and study the effects of the bond. And so this is the thing here. Here we're going to test this length of the region of bonded FRP and see what happens. And this was done in static tests and later in dynamics. This is painted a speckled pattern color because I'm taking some fancy optical measurements here and tracking displacements and strains, full field strains, using a technique called digital image correlation. And this allows a very robust measurement of strains rather than a simple array of strain gauges might get, and to fully sort of explore the nature of the bond. What we can see from the static cases is in the best case scenario, we were getting debonding strains between 0.45% and up to 0.7%, but usually averages around 0.5%. As we progress in load here, so as we start to load this up, these different curves here represent the strain distribution along the length of the prism. Here's the join between the two prisms at different load points. So here we're looking at, if we look at H here, this is the point, where is H? Right here, for just a random point. So at H, all this region over here, this region here, has already debonded. And it's just FRP and pure tension. It's not composite to the concrete already. So here's a progression of debonding over the length. This is our this is our development length, and over here is the rest of the FRP that isn't stressed. And so what we did measure is there's about a 50 millimeter development length for this material, which is what we expected. Now if I take this and I go to high strain rates. Oops. Let me go back. Maybe. Yeah. So a high strain rate test, a drop mass test. We took a big piece of steel and dropped it onto a mechanism here that allows a vertical load to go on it and to pull horizontally. And here's our specimen. And what we're studying is the development length here and using an optical measurement of that. So here's after debonding, and here's the test itself. And so this is the optical measurement of strain. This is the strain field, and the colors represent the strain itself. Looking at this, this is 4,000 times slower than real time. Here's the boundary between the two prisms. So we've got the other side of the prism here, and we're pulling apart there and way over there. And in here, this is the bounds of the FRP. Well, here's where the failure is, so you can start to see that. If I take a slice through a point in this, we can see that the strain versus time history that comes out of this, and we get a strain rate at this particular region measured at that spot of 4.6 strain per second, but depends on where you're measuring and how you're measuring exactly what that strain rate would be. Now, over time, we can look at the progression of a line of action of strain along here to look at the bond. At an early time, we get areas with no stress or strain upon it. We get a pretty low amount of strain on this. Over here there's a tension crack that formed between the two prisms, and down here is our development length. And then later on, we get this sort of plateau up here of the debonded area, development length, no strain. And then further, and we're starting to strain the very ends of it, and then at failure. So from this, we can gain some information. We get up to about 0.82% strain, but the development length remains around 50 millimeters or so. And this implies to me that there is potentially, and I'm going to really guard my words here, one test is even fewer than the two that we were drawing conclusions from before. So this is ongoing research, and I've got 50 of these things to do. But all I'm showing here is one, so it's too early to draw conclusions. But based on all the static tests, and the worst I ever saw was a strain up to 0.7. In here we get a strain of 0.82%. We are seeing potentially an increase in bond stress under high strain rates. So the stress would be related to the sort of the derivative of that strain distribution, which means that we could potentially apply a higher strain design for FRP bond, potentially. We can't yet. And this goes to discussions earlier. If we want to do a probabilistic design, we want to look at the moment capacity and the flexure capacity and make sure that we are designing that to its probabilistic amounts so that we can accurately assess shear capacity. We need to include things like the potential of a dynamic increase factor for bond of FRP. And here from this only one specimen, we can say that maybe we should have multiplied the strain at debonding by a factor of 1.28 under the strain rate in this particular region. So here, conclusions. I wasn't looking at you for a while on purpose there. FRP jackets can enhance ductility, and they can allow for higher design limits. They You can strengthen, but you should be careful that you're not compromising ductility capacity for your column design, because if you do that, you're going to really hamper yourself for how far you're allowed to design to. And potentially, there's some evidence building that maybe there could be a dynamic increase factor for bond in the future for FRP under high strain rates. That's what I have, and thank you very much for your time.
Yes. I have a question. Thank you for the presentation. Very, very nicely done. But this one variable that you didn't talk about,
Sure.
which is heat.
Yes.
The heat developed by the blast.
Yeah.
And how that influenced the development of the CFRP.
Sure. So
And I saw that,
yeah. No, go on.
just one second. And I saw that you're protecting the column from the heat because you're using a panel
Yeah.
to get the glass. I'm not sure if your experimental setup allowed for heat generation of anti-direct heat.
So this was a simulation using a shock tube, and the shock tube only used driven high pressure air. So we pumped air into a driver section. There was no detonation, no gas detonation or anything like that to drive it. So the actual test, there was no heat. It was ambient temperatures, and it represents a far range explosion if you were to put in all the factors associated. Sorry?
10 meters or?
The distance, I would say further away than that even. Far enough that heat wouldn't be an issue for this type of test that I'm doing. Now, if heat is an issue, of course, you're going to have to worry about protecting your FRP. But I would probably argue that the heat would take a bit more time to affect the FRP and the resin and the bond than the actual action of the blast and the response of the member. Because here we're looking at several milliseconds rather than complete seconds that even a very high temperature heat would take to start to soften this material.
What is the equivalent TNT that you're using in your test?
Well, I off the top of my head, I don't have that one for these ones. I'm sorry, but it's tremendously variable. And then there's the question of the low transfer device that we had was about 13 times wider than the column. So the equivalent TNT depends on how you factor that in, because there's a tremendous amplification of both pressure and impulse with that. But what I can say is it's high TNT values, very far away. So standoff distances are quite big.
Very nice. A suggestion. In terms of the connectivity of the CFRP, you're using some sort of epoxy or adhesive.
Sure.
What about mechanical connections on top of?
Sure.
The
And that is absolutely something that should be concerned, that you should be concerned with. In fact, back to the Canadian thing in CSA S8 06, which is the design for FRP, it says you can design up to this limit for flexure unless you provide some sort of anchorage, and then you're on your own for that part. This didn't include the anchorage thing, but anchorage is the obvious next step past studying the nature of the bond.
I see results. I think with the mechanical connection, you probably get
Yes.
much better results.
I agree.
Number of hoop wraps, how do you calculate?
Yeah, so I don't have this one in here, but the number of wraps for ductility can be based off of a performance-based seismic design standard. At least this was where we sort of left this particular project. So based off of that, if you take the relationship between how far you want to drift and the level of axial load, you can then compute and a built-in confinement model essentially. It's a very empirical equation. You can compute the amount of internal transverse reinforcement that you need in the hoop steel to gain that ductility. Now, taking the same equation and then modifying the properties of steel into FRP and applying that to the surface, and this is I've done this a few years ago, but basically you can say for a level of seismic ductility demand, you need X thick material given your FRP is this property.
That's based on displacement. It's like adding stirrups.
Yeah, it's a it's a performance-based design based on the concept that you want to gain a ductility of, say, 4, then you can go back and calculate the number of, or the area of the reinforcement that you need to do that. And it's the same. For these columns, I used a 10 millimeter aggregate because they were somewhat smaller and there wasn't as much cover distance, and I wanted the aggregate to go everywhere. So 10 millimeters is 3/8 or so.
All right, very good. Thank you.
Thank you.